So good day, Merry Christmas. Now I want to explain a very beautiful article, lexical generalization in CCG grammar induction for semantic parsing. But I should say that wrong supertags results parse failures. Just like part of speech that we assign to each word part of speech, here we assign to each word a supertag. For example, supertag of flies is S on the left NP, and so on. But if we just write any supertag, it may not work for parsing, because here, for example, we say that even if this works, but the next one doesn't work because S does not combine with anything on the right. And that's a big problem. So not only supertag is important, but also the parsing is important. It should match the parsing. Otherwise, there is a parse failure. And he's an amazing scholar. Very nice articles. And so this 2011 article is really important. Of course, many of these articles use these log linear models, discriminative log linear models. Z is here is the logical form. Y is the parse, our parse, because we can have many parses for a given logical form for a sentence X. And so what is the motivation of this paper? First of all, traditional CCG lexicons list lexical items that pair words and phrases with syntactic, that supertag, and semantic content, that logical form. Such lexicons can be inefficient when words appear repeatedly with closely related lexical content. They introduce factored lexicons which include both lexemes and templates. So I will explain what are these. For example, in a flight booking domain, we might have access to training example. For example, our X is here and Z is this logical form. X is a flight, so this is a true. So given an entity, it gives me a true a Boolean expression. So this is the type of that. And from X, and so X from Boston. Boston here is logical constant. So this is constant in lambda calculus. So this is the learned lexicon. After training, we understand that these should, but it's very boilerplate. For any of these words, we have three different forms. All of them are almost the same, but only one word changes. So we want to compress it somehow. We want to summarize it. We want to compress it. So there is a beautiful approach in this article, in that for lexeme, light, and flight, so flight is the word, and this lexeme, we say that, okay, for this we have, for example, here, if we ignore the first one, the last one, we say that we have two different approaches for we have two different templates. We can include the last one as well, because one of them is getting repeated only. So when we say flight, word and flight, so this one, so if we just replace V1 with flight, so it's a list. It could be many things, flight and anything. For just lexeme. For example, here we say from Boston and many things. So if we just replace V by flight, then we can generate all of these things. So you see that we just need to see which template you want to use. And that's the compression that I was talking about. So these are called factored lexicons. And the problem I want to show is that we have XI, we have many sentences we have N sentences. For example, one sentence is show me flies to Boston. This is X. The Z, the logical form is as follows. So we want to learn this. Not only this, but we want to also learn the parse as well. So to model that, we say that we have a lexeme. We want to map Boston to Boston MP Boston. This is the final lexical entry. And so, for example, we want to say flights from Boston. The super tag for this is MP. This is NP. As I said, this means that it needs an NP on the right to give you /n, and then N needs an N on the left of that, and so on. So that's why we can combine these together using we have 4 rules: forward, backward, forward composition, backward composition. And so when we say type, we should know what we are talking about. For example, I told you that this gives you when you give a entity to it, it returns a Boolean expression. So what is the lambda cat? What is this type? So these E could be, you see, entity, T could be truth, and sometimes we can use numbers for different examples. So a new way of representing lexical items is that we can say it's lexeme and template, as I explained before. And this is a compressed version of that. So what is the idea is that we want to say what is the probability of a given parse and given logical form of a parse and logical form given your sentence X. And we assume that we know until now what is the lexicon and what is the parameter of your new model. So log linear models are very powerful. What is the probability of this par y given x? For example, I'm just talking about the abstract log linear models. So you see we have a v vector and f is the features. It's very important that x could be, for example, for input, y could be your output. For example, in our case, we have another thing, v. We have different outputs, so we have 2 kinds of outputs because structure prediction. But we have the features, v1, f1, v2, f2, because we need different features. Because we want it to be more expressive, the more features we get. So we need features in this beautiful log linear discriminant model. So there are two sources of features. One of them comes from your lexical features, like this, lexeme and template. As I said, this is the compressed form of that. And we represent it by binary. So it becomes matrix, for example, the Lth row and the Tth template. But, we can just vectorize a matrix very easily. Just vectorize it. So it's a good feature. And how about the logical form? They also provide good features. So let's say we have another feature of phi2. And what we represent is that each time a predicate P takes an argument A. Because we have some predicate, some arguments, and so we can create, again, binary indicators. And then we can, when we have a matrix, any kind of matrix, or even tensor, we can vectorize it. So we have a good feature. And because we have features, so we have these here is 2. We have 2 features, but each feature is a vector. And now we are ready to do log linear models. But log linear models, this is what I think. So this is the known lexicon, and we want to maximize its probability and for a given x. For example, for one sentence, what is the maximum? What if for another sentence, what is the maximum? And because we have many parsers, we sum over that. Because there are many parsers, just like context-free grammar, if you remember in my playlist, we had many parsers because of that ambiguity. And here we have, again, some ambiguity. We have many parsers. Which one? But all of them leads to this logical form Z. And we just marginalize it like that. So, as I said, we have this probability of Z given xi. So call it output I. So in any, when you want to learn this, we need the gradients of that. So this is the gradient. And if you just replace this part with delta, then you can say that you increment it, and this is the step for learning, and so on. So the algorithm is, first we start with the only thing that we know is that your sentence, this is your sentence, has the logical form, nothing else, and this is the start. And also, of course, you know that Texas is represented by this, comes from this lexeme text, nothing else. Then we build what is, so we have the root. So what we know is that the leaves here, and also the root. So we want to infer what is possible about this, because this is, if we know that, then we have the parse. So to do that, we update the lexicon with something called after new lex. And I will explain what is new lex. So here, as I said, when we say New York borders Vermont, we want to split it, because in order to have better generalization, if we just imitate and memorize things, it doesn't become interpretable. But we love interpretable AI, so we need to generalize it. So we love these compositions, and so we try to split them like this. We split it to two of them, Vermont and this one, New York borders. And if we do that, this is something called restricted higher order unification. Just like category theory, we can combine functions here. We can combine them together, f and g, like f of g for any h. So we split it into f and g. We find pairs f and g. And of course, because there are lots of splitting ways, so we try to create some rules such that it reduces that. So the motivation of these three things is to reduce the number of splittings. So there are many splitting categories. As I said, you give an entity, you return a Boolean expression. So you are familiar with these things, but these are good features. For example, what are the splitting that we can do? We can say we can do forward application. We can do backward application to split it. We can use forward composition to split it. We can use backward composition. So there are just four things that we can use. So there are many different ways to, but we wanna learn which one is good for a particular sentence. And that's why this is an example. From span 0 to n, the words of a sentence, we span it into 0 to I, and then I plus 1 to n. So we have different categories, and again, they go on forever. And they go on until they reach the final leaf nodes. And so the algorithm is like this. Introduces new lexical items, this new lex, which allows for the possibility of a parse where the subtree rooted at C is replaced with this new entry. So we want to discover that. So this is the parameter update. As I said, after that, we need to update the parameter theta. If you remember, theta be delta. And, it's here. So if you update this, then the next time that you want to go through that, you have a better model, more realistic model. So this loops forever until we learn not only the parameters, but also the lexicon, which is our goal. Because each time we add new thing to our lexicon, expand the parameter vector to contain entries for the new lexical items, as I told you before. So each time, but we initialize with the only thing that we know, because we know that the start of that is this logical form for a given sentence. And now this is for English. What we have learned for English? Joe 250 lambda calculus datasets. This is a really interesting article. Weakly supervised things and unsupervised things is the future of these machine learning, because we need to understand we are very good at supervised learning, but we are not good at reinforcement learning. We are not good at unsupervised learning. We are not good even at semi-supervised learning, because these are natural problems that every child, the brain of each child is learning. This is how it learns.